Well, good afternoon, everyone, and welcome to today's webinar on enhancing the efficacy by tackling spray water challenges in the tank. My name is Brian de Villiers, and I'm currently working as a consultant for villa crop protection after I spent about 17 years full-time with the villa team. Thank you for joining us today. I trust you will find this session insightful and valuable as we discuss how spray water quality can impact product performance and efficacy. And yeah, just a special word of welcome to everyone that's tuned in today, everyone from South Africa. I know there are people from Zambia that are in the webinar as well, so welcome all of you. Just a few house rules before we start off the presentation. The first thing is, you'll see I'll put off my camera just as I start the presentation. If you don't mind, I'll put it on again once we do the conclusion right at the end. And then just a thing about questions. If you don't mind, if you have questions, I think it will be better if we discuss the questions afterwards. You can phone me. There are my contact details, or you can email me, and then we can discuss it in detail. So yeah, we're probably not going to have a question and answer session at the end of the webinar, but you're more than welcome to contact me on that cell phone number or on my email address. And then another thing that I'd like to say before we even start the presentation, I'm going to show you a lot of photographs today of trials that were done with adjuvants, and then your immediate response will probably be, but look how poor the control is. But I just want to explain that this is how we do adjuvant trials. If we want to see the differences between adjuvants and we really want to determine the influence of water quality, we normally cut the rate of herbicides especially to show those differences. So you'll see in some of these slides there's going to be very poor control, but rather focus on the differences that we get there. Okay, good. So yeah, there are my contact details. Like I said, you're welcome to contact me at any time. Just a bit of content about today's presentation. First of all, I'm going to give you a bit of background as to why water quality is so important. The first step, and I think after I've showed you a few slides, you'll realize that water quality is probably one of the main factors when it comes to the efficacy of some products. And then just to show you a bit about what Villa specifically does about water quality, how we warn the end user about what has to be done about water quality. And then we're going to break up the presentation into four components basically. First of all, we're going to talk about cation antagonism. And when I talk about cation antagonism, that's salt antagonism, it's also called. That is basically the antagonism of especially certain post-emerge herbicides by antagonistic cations that are naturally dissolved in water. Like, for instance, calcium, magnesium, sodium, potassium, for instance. So that's what we're going to do under cation antagonism. So that's mainly about herbicides. Then we're going to do a whole section on pH, why pH is important, why we use buffers, but also a few warnings about where a low pH, sometimes caused by buffers, but sometimes also caused by other components in the spray tank, where these products can have a really negative influence. We can't talk about pH unless we've spoken about buffering capacity. Now, buffering capacity always goes hand in hand with pH. Buffering capacity is the ability of water to resist a change in pH. So therefore, you're using a buffer, for instance, you think that that you're decreasing the pH to a certain level, but because the water has a high buffering capacity, the pH doesn't go down as much as what you suspected. It's not acidified enough, and then you have problems. On the other hand, a very low buffering capacity allows the water to be acidified very easily. And then lastly, I think there's only one slide about that. We're going to talk about turbidity of water. In Afrikaans, troebelheid van water, how the clay minerals, the organic matter that is suspended in water. Okay, so let's begin and set a bit of a background as far as water quality is concerned. If you look at various companies' labels, but especially the Villa labels in this case, you'll get a very good clue as to products that are sensitive to some form of water quality. And I've got three of them that I'm going to show you today. So Glygram or glyphosate, the dry formulation, but it could have just as well been the liquid one. The Glygram 710 SG has got a specific statement on there that says always use clean water, avoid the use of brackish or muddy water or water with a high colloid content. So that gives you a good idea that this product is influenced by cations in water, maybe mud in water as well, and that you must take the necessary steps to avoid that. The first thing is use a better quality water, but what's especially important is that you use the correct adjuvant. There's the next one, which is a Villa insecticide with the name of Judox or Judo X, which is a mixture of indoxacarb and a pyrethroid. It says there on the label, there's a statement on the label, use Komodo buffer at the registered rate to adjust the pH of the water if not in the ideal range. So this gives you a good idea that some component in this formulation is influenced by pH, and it's maybe degraded in the spray tank by a low pH, and therefore it's important to use a buffer with this product. And then the last one is Disrupt 200 SL, which is a diquat herbicide, and that says do not use muddy water. Now diquat is a bit different to a product like glyphosate, for instance. It's not really influenced, as far as I know, by cations in water, but rather the muddy particles that you find in certain water sources. So this always gives you a good clue as to what the product is sensitive to. I've only got three of the products that I've listed here, but there are various other products, especially in Villa, like certain sulfonol ureas, the certain imidazolinone products, certain phenoxy herbicides, etc., that have got statements like this on the label. Now, why is water quality so important? And this is an important slide just to show you the magnitude of the influence of water and spray water on the efficacy of products. We've got three phases that we've got in the spraying process. First of all, we've got the spray solution phase. Then we've got the spray droplet phase, and you'll remember that the last webinar that Voltan did was about the spray droplet phase. And then the last phase is the plant phase. Basically, what crop protection products and adjuvants do in those three phases. Now let's just give a bit of explanation about each phase. If we look first of all at the light blue phase, the spray solution phase. So that's when from when you mix your crop protection product in the spray water, whether it be in a mixing tank or the tank itself, doesn't matter, until the droplet has fully dried on the leaf surface. And this is where we often make a huge mistake. We think the spray solution phase is just in the tank. It's not just in the tank. It goes much further than that. It goes to on the leaf, in the droplet, and further reactions occur there as well. And if we realize that these reactions occur, we'll be even more careful with these particular products. And then the spray droplet phase that you did the last time, that you guys that tuned in last time to the webinar, the spray droplet phase is from when the droplet is released from the nozzle until it impacts the leaf. And then the plant phase is from when the droplet impacts the leaf till the process is completed, till all the herbicide or its systemic other products, insecticide, has been absorbed, or the contact action has been finished, etc., etc. So that's the plant phase. But one thing that you can see there very, very clearly is that the spray solution phase, it encompasses the spray droplet phase. So the spray droplet phase is encompassed in the spray solution phase, and a big part of the plant phase is also encompassed in the spray solution phase. And this is why the spray solution, and this is why pH, cations, the adjuvants that rectify them are so vitally important, because it's such a plays such a huge role in the whole efficacy process. Now, although I divided them into 3 phases, it's actually just one application process. And it's so intertwined, these different phases, that the one influences the other. So from when the product is mixed in the tank till the process is completed on the leaf is, I call, the application process. Even after, some of these reactions happen long after the tractor has passed over or the sprayer has passed over the crop. So water quality is important from mixing in the spray tank until the droplet has dried. And I'm going to emphasize that again, until the droplet has dried, because this is where we often miss things, and we think that if everything mixes nicely in the spray tank, that it's going to be fine when it's on the leaf, and that's not always the case. So let's give you an example. Say, for instance, there's a grower that applies this mixture. He's got 3 crop protection products that is mixed in the spray tank or in the spray water. He's got a foliar nutrient in there. He's got a buffer, because one of the crop protection products recommended a buffer, for instance. He's got a surfactant for the same reason. There's a product that recommended a surfactant. And then he's used a product like Interlock, for instance, which is a deposition agent. So he's basically got 7 components in that spray tank. And I think all of you will agree that this often happens. This is a thing that often happens. These type of mixtures are not uncommon with a South African grower, and we've seen more complicated mixtures than this. The important thing to remember, however, is, as far as water quality is concerned, is dissolved and suspended particles in water do not disappear. So they're present in that spray solution, but they will also be present later as the droplet dries on the leaf surface. And if I had to ask people how many crop protection or how many components have we mixed into the spray solution, or how many components are there in the spray solution, I think most of you will say 7, 3 crop protection products and 4 other products. But the answer is actually 8. Water is another chemical in the spray tank. Water has a pH, water has dissolved cations, and water has buffering capacity, and that all influences the efficacy of other products. Now, like I said, dissolved and suspended particles in water do not disappear. Once you've sprayed the spray mixture and it lands on the leaf, obviously the products are not separated. They do not lie apart. They are actually intermingled. So they all mix together on the leaf. And there's also cations, there's mud in some cases, organic matter, it's got a certain pH, etc. And this is where further reactions occur, because if you just think that water droplet is going to start evaporating on the leaf, and as it evaporates, the solubility of products is going to be limited, and they're going to start reacting with each other. And if you're applying an antagonistic tank mixture, or if you're applying a poor spray water, then you're going to see the effect of this. Now, when people get a spray water analysis report back from the lab, it's often extremely intimidating. And you can see that's just an example of a analysis report that we got from BEM Lab at that stage. It's 2 water sources on a grower's farm, for instance. You can see all the components there, etc., etc. I just want to tell you that this is one of the water sources that I've seen that had the most antagonistic dissolved salts in there. So it was a pretty bad, or both of them were pretty bad. But there are just a few things that you need to look out for on an analysis like report like this. And then you'll see it's actually quite simple. It's quite simple what you've got to look for. And I'll give you a few threshold values just now that can maybe help you a little bit. But let me show you what's important. The first thing that's important is your calcium, magnesium, your sodium, your potassium, and certain heavy metals like iron, for instance. Heavy metals are normally not a big issue, but the 4 other cations, the calcium, magnesium, sodium, and potassium, that's what makes waters hard if it's got a high calcium and magnesium content, or it makes water brackish if it has a high sodium content, for instance. And those cations influence herbicides, for instance. If you don't do a full water analysis report, you maybe just have EC, or total dissolved solids, as a single measurement. That's also a good indication of the amount or the concentration of dissolved cations in the water. So for instance, if you have a look at the velocity dry max label, you'll see there that either Villa asks for in some cases now for a full water analysis, or just an EC measurement to look if your rate is in line with what you should be applying. EC, for instance, is not as accurate to say exactly what cations are there, but it's a pretty good measurement as well. The next one is pH. pH is a very important factor, but probably one of the most overstated factors and overrated factors as far as crop protection products are concerned. And I'm very much a believer in the correct use of buffers to correct pH under certain conditions and with certain products, but I think they're often overused, and I think they can cause problems. And I don't want to stand still with buffers. I want to also say that other products that we are mixing into spray tanks that also acidify the spray solution a huge amount, like for instance overly acidifying foliar nutrients, can also play a huge role. And I'm going to show you some examples later on of what the problems can be. The only anion that is important is bicarbonate, HCO3. And HCO3, or bicarbonates and carbonates to a lesser extent, but normally carbonates are not present, as you can see in this water. It's mostly bicarbonates. That works together with a pH. So therefore, if you've got a high pH, for instance, this water's pH is 7.6 or 7.5. If you go and look at the bicarbonate levels, that's 466 and 567. That's particularly high. So that means if you've got a pH of 7.6, don't think that you're going to reduce the pH of this water very easily, because of those high bicarbonate levels that gives it that buffering capacity and that resists a change in pH. Now, the high buffering capacity can be a bad thing under certain conditions, and maybe even a good thing under other conditions. And if you stick around, I'll show you a bit later exactly what the effect of buffering capacity is. And then the last one is turbidity. And I think this one it goes without saying, is the dirtier the water is, the higher the amount of clay minerals, the higher the amount of organic matter in that water, the bigger the problem is going to be. So so clean water is, I suppose we can all argue about the definition of clean water, but surely we do not want muddy water or water with a high organic matter content. Okay, let's start with the first one. So we're starting with the first one, cation antagonism of herbicides by hard and brackish water. Then the next one will be pH, buffering capacity, and the last one will be turbidity. But let's start off with the cation antagonism, and it's probably the biggest part of today's presentation. Now I've got a glyphosate slide there, and before I carry on, I'd like to say I've got a lot of glyphosate slides under this heading today. But that doesn't mean that glyphosate is the only herbicide that is influenced by cation antagonism. Many other post-emerge herbicides are influenced as well. I'm just using glyphosate because it has been researched so well, and that's where I had the most visual material. But other products like clethodim, certain sulfonylureas, phenoxy herbicides, some of the imidazolinones, the list continues. It's a long list of products, post-emerge herbicides that are influenced by cations in water, in spray water. But let's just have a look at this one. We've got 3 pots there. It's self-explanatory. One rate of glyphosate was applied over all 3 pots, exactly the same rate, but you can see the difference in control. Distilled water on the left at this particular rate, and like I told you in the beginning of the presentation, it was a pretty low rate because it was a glasshouse trial. But with this particular rate, you could control the weeds almost 100%. Where you applied with hard water that contains high amounts of calcium and magnesium, or brackish water that contains high amounts of sodium, you can see the difference in control. So this is what water quality can do. And now the huge differences here, you're not going to get these type of differences in the field. But I've seen differences of 10%, 15%, 20 and 30% in the field when glyphosate, for instance, was applied with poor quality water and nothing was done about the problem. Okay, let's talk a bit about glyphosate. And remember, when I talk glyphosate, we're talking all these other herbicides as well. That's just a glyphosate molecule, what it looks like. It's not important exactly what it looks like, but what happens with cation antagonism of herbicides? Does it happen in the spray tank? And the answer is no. Cation antagonism of herbicides does not happen while the product is solubilized in the spray tank. And the reason for that is when everything is solubilized in the spray tank, there's enough water to keep everything in solution, and there's no to little binding of cations with a glyphosate molecule. But as the droplet dries out on the leaf, you sprayed now, the droplet's lying on the leaf, it's busy drying out. And you've sprayed, for instance, with a hard water, calcium water, but you can replace that calcium with magnesium or sodium or potassium as well. What happens to that glyphosate molecule on the leaf? And this is basically what happens. It totally warps that glyphosate molecule. Calcium, because it's a divalent, a double positive charged cation, or magnesium have that effect on the glyphosate molecule. So the glyphosate molecule has totally been changed. And because it's been changed, it totally alters the action of that particular product. Now sodium will look a little bit different because sodium has only got one positive charge, but sodium is about 60% as antagonistic as calcium. So it's also vitally important and very important in South Africa because it's found in such large quantities in certain areas. So I said it all happens on the leaf. I showed you now what happens to the glyphosate molecule. Let's see what it looks like in practice on the leaf. So this is basically glyphosate spray droplets or spray droplet residuals that have dried out on the leaf surface. So there's no more water in these spray droplet residuals. And then we took scanning electron micrographs. It's 500 times enlargements of a dried out glyphosate droplet. On the left, it was applied with distilled water. And the 59% is the amount of absorption, the percentage absorption of that glyphosate that we got when it was applied in distilled water. As soon as it was applied in calcium, in high calcium water or high in hard water, you can see the physical characteristics of that spray droplet residual changes. It becomes thick, it becomes amorphous, it becomes it doesn't lie nicely in the walls of the the plant, of the cell walls, and there's very poor contact, and therefore you get very poor absorption. So 59% with distilled. What did we get with a high calcium water? 1%. Now, this, like I said, this is a very extreme example once again, but that shows how devastating the effect of antagonistic cations in spray water can be. But it doesn't happen in the tank, it happens on the leaf surface as that droplet is drying out. Now this next slide, I don't want to say you must take it with a pinch of salt, but these are just the guidelines that I use. This is not published data or anything, this is just what I believe. Often people ask us, but what are the threshold values? How much calcium and magnesium or how much sodium must there be in the water before you've got a problem? And my answer is always, if you've got 1 part per million in there, you should already be using adjuvants. Because adjuvants have a very positive effect, even in the absence of these antagonistic salts, and especially ammonium sulfate adjuvants. But if you want to use fresh thresholds, I say if calcium and magnesium, that's how hard the water is above 100 parts per million, then you can start having serious problems. Or sodium plus potassium is above 100 parts per million, same story. But then I want to say it's an additive effect. So therefore, if you've got 25 parts per million of calcium, which is very low, and 25 of magnesium and 50 of sodium, then you've already got a problem. So you don't need very high cation levels to see the red lights flashing and to start use adjuvants probably as a standard practice to overcome these problems. And then the next one is if the EC goes above 100 millisiemens per meter, then you can start having serious problems. But like I said, take these threshold values. This is really not data, not based on any data. It's just by experience, and this is what we've seen out in the field. And these are normally the threshold values that I work on. But I'm one of those proponents of using adjuvants as a standard practice when it comes to ammonium sulfate, especially. Now, the reason why ammonium sulfate is so effective. Remember I showed you, I'm going to show it to you now again. On the right is that distilled one. That was glyphosate alone in distilled water. And then you saw the one that had the calcium in the water. Now the one on the left on this slide is glyphosate plus hard water. It was the same as that the one that with the calcium in, but we had ammonium sulfate in here. Now I can see two things in the spray droplet residual. The first thing, in the bottom corner or the bottom half of that spray droplet residual on the left, you can see star-shaped crystals. Okay, and those star-shaped crystals are calcium sulfate. So something tells me that the calcium has been precipitated at leaf level and bound to the sulfate, and that has enabled your glyphosate spray droplet residual, the rest of that spray droplet residual, to physically look very much the same as it was in distilled water, thereby increasing efficacy and eliminating the effect of cation antagonism. Now, the chemical success story of ammonium sulfate, and you will realize from today's presentation, I am a fan of ammonium sulfate still. Why does ammonium sulfate work so well? And when I talk about ammonium sulfate, I'm not talking about fertilizer or any other product that hasn't got an L number. I'm talking about spray grade ammonium sulfate that has an L number. I'm not going to go too much further in that, but those are the products that I'm talking about. The chemical success story of ammonium sulfate is calcium, instead of binding to the glyphosate, rather binds to the sulfate to form calcium sulfate, which is very insoluble. It's gypsum, and that precipitates at leaf level. The same reactions happen for magnesium and sodium and potassium. I'm not going to go into too much detail, but it's important that these cations are precipitated before they can react with the glyphosate. And this is why ammonium sulfate works so well, because it handles all four of those antagonistic cations. The next thing that I'd like to say is it's a complete reaction. Okay, I'll get back to that just now. It's a non-reversible reaction. and the same principle applies to those other cations, like I said. So let's stand still at the complete reaction and the non-reversible reaction. What I mean with complete reaction, if you have used a high enough rate of an ammonium sulfate containing product, then you will neutralize all those antagonistic cations. It's a complete reaction. It's non-reversible. So that means once it's done, it can't go back again. It's not like a chelating product, for instance, that there's a balance. This is a non-reversible reaction, and this is why ammonium sulfate is so important to us at Villa. And then also I'm showing the glyphosate molecule again, and when you're using ammonium sulfate, that enables the glyphosate to be absorbed in its most absorbable form, which is that one. So what is the effect on weed control? Okay, so this is these aren't weeds exactly that we're spraying on, but it was test plants that were planted and we sprayed glyphosate over them. And I think you'll see why we are such believers of ammonium sulfate containing product. So that was hard water. The first one was untreated. The second one, the middle one, is hard water, and with glyphosate at a certain rate. And then exactly the same rate of glyphosate, but with an ammonium sulfate product. Now, this particular ammonium sulfate product didn't even have extra surfactant or anything in there. It was just ammonium sulfate. So this is what ammonium sulfate can do for you. And once again, not fertilizer grade ammonium sulfate, a spray grade ammonium sulfate. So that's how effective it is. So I'd like to make a statement. Villa only believes in ammonium sulfate based adjuvants to address cation antagonism. With all our herbicides that are antagonized by cations, we only believe in the ammonium sulfate based products. And there are two products: our premium product, Class Act NG, which I'll go into a bit more detail later, and Velocity Drymax. Class Act NG has also got surfactant and humectant in there, where Velocity Drymax is just a dry, good quality ammonium sulfate product. So those are the only two adjuvants that we believe in with these particular herbicides. Okay, let's show you some data. Just like any other company, Villa would love to use other products that are just as effective as ammonium sulfate, but that we can apply at a very low rate, because then obviously the transport costs, things is in, which is very, very important these days, etc., etc., etc. And this is the reason that we believe in ammonium sulfate. So this is a trial that we had done by the ARC, and it's the data of that particular trial. So it's percentage control on the left there, and you'll see glyphosate control was poor, and I've explained that already to you. So glyphosate alone was green, is the green bar, and then those 5 red bars are Velocity Drymax applied at different rates, and the one on the right was a low rate ammonium sulfate replacement product that we're going to call product X, for instance. Okay, so let's go through this. There where I've circled those 3 bars, that is ammonium sulfate. That's the registered rate range of Velocity Drymax, just to give you an indication. So you can see it's head and shoulders above the other product. But what I'd also like to show you is if we then applied reduced rates of Velocity Drymax, unregistered rates actually, which I wouldn't recommend, to see how that compared with an ammonium sulfate replacement product. And those are the 2 blue arrows. The left one, Velocity Drymax, at 25 grams per 100 milliliter. That's nothing, and I'll never ever recommend a rate like that. But that was more effective than the other product. At 100 grams per 100 liters of water, once again, a rate that we would never recommend, it was even more effective than the other product at the same rate. We weren't happy with these results, so we decided to take it out to the field, but we didn't test just one replacement product there. We tested 2 ammonium sulfate replacement products. So it's a repeated field trial. So there were 2 trials done in different areas on Chenopodium, and it was done by Curativo. So control on the left again. This is glyphosate, is the green bar. Class Act NG, the yellow bar. Product X, ammonium sulfate replacement product, the grey one, and the pinkish one on the right was a product Y. Both of them at the recommended rates for that particular water quality. But we didn't want to discriminate against these products because we felt that Class Act NG also has a surfactant and a humectant in there. So what we did is we added extra Villa 51 to these other products so that we could compare apples with apples. And I think the results speak for themselves, that there's a huge difference in control. And lastly, this is why we're sticking to these ammonium sulfate products. Okay, just a little bit about multi-component AMS products. Often we get ammonium sulfate that is mixed with other components in the formulation, and it's a one product does it all. Class Act NG, for instance, is ammonium sulfate plus a full rate of surfactant. So it's as good as you applying a full rate of Villa 51 plus that, plus a full rate of humectant, which reduces droplet drying or increases droplet drying time. That's normally what we use if we want to use a surfactant, or we use Velocity Drymax and sometimes add Villa 51 to that. Please be careful. If you are using products that are multi-component adjuvants, make sure that they don't just contain the ammonium sulfate, they must contain enough surfactant and enough humectant in there. We must remember there's limited space in formulations, and it's important to know that all the components are enough for that glyphosate product or one of the others that we applied with. The last thing, Villa stance on acid in the formulation. Sometimes people want acid in a adjuvant formulation, especially for glyphosate. We don't believe in that at all. We believe that buffers are normally not necessary with glyphosate, for instance, and many of these other herbicides, and unless specifically recommended. So we decided rather to have sufficient ammonium sulfate in there without adding extra products that would take space in that formulation. Okay, we've spoken about hard water and brackish water. Soft water also has challenges. We often think it's only high salt content water, but often soft water also has challenges. And this is one of the challenges of soft water, is excessive foaming. So if you in an area or you find that a lot of your clients have excessive foaming issues, it's probably because your water quality is so good that you get these foaming issues. Good, we've done the cation antagonism, and we nicely on time, I think. The next one is the pH that we're going to be talking about. Now pH is especially important for some insecticides because they are influenced by alkaline hydrolysis or the breakdown of insecticides in high pH water. But it's firstly important to know how the pH scale works. And the first thing that we should know is the pH scale is from 0 to 14. The lower the number, the more acidic; the higher the number, the more basic. And if, for instance, you're using buffers or other products that decrease the spray solution pH just by 1 pH point, from 7 to 6, for instance, what you are actually doing is you're increasing the acidity levels tenfold. If you are reducing the pH by 3 pH points, from 7 to 4, what you're actually doing is you increasing the acidity level 1,000-fold. So that means this is why buffers are so effective to reduce alkaline hydrolysis, but this is also why pH reducing products can also be devastating, if they are not used correctly. So let's try and show you on this. I said to you, alkaline hydrolysis is the ability, or is the degradation of insecticides, for instance, or some insecticides in water with a high pH. So just to give you an example how alkaline hydrolysis works, if we look at the alkaline hydrolysis of a product, say it's an insecticide with a half-life of 1 hour. In the pesticide manual, we can normally see what the half-life of these products are, but let's look at the alkaline hydrolysis with this product with a half-life of 1 hour. After 1 hour in the spray tank, 50% of that product has been degraded, is gone. After 2 hours, another 50% of that 50%. And so we can carry on 3 hours and 4 hours. So if this product has a half-life of 1 hour at a certain pH spray water, if it lies in that tank for 4 hours, you're only going to have 6% of that product left. So this is why alkaline hydrolysis is very important, and this is why the use of buffers is important. But please, this is an extreme example. Most products, about all products, are not this sensitive to alkaline hydrolysis. But I always say, if you're just losing 5% of the product, that could be the difference between acceptable control and unacceptable control. So that's why it's important to use buffers. However, there are some disadvantages of a low pH. And the first one is solubility. This was a sulfonylurea herbicide. It's once again those spray droplet residuals. I'm not going to explain too much. And the bottle on the left there, that was the spray solution at a pH of 7. That's the spray droplet residual, what it looked like on the leaf surface. We got 73% control in this particular experiment, which was also not great, but that doesn't matter. Let's rather look at the differences. When we decreased the pH to a pH of 5, that's what the spray solution looked like. It was totally out of solution. The spray droplet residual looked very different. It was grainy. It was there was a crusty deposit on there that's never going to be absorbed properly in any case. And we only got 56% control. So a low pH could limit the solubility of certain products. Sulfonylureas are a prime example of that, but there may be some others as well. And it's important when using buffers, but even more importantly, when using products, foliar nutrients, for instance, or other products that are mixed in the spray tank that are very low in pH, watch out for this problem because it could influence efficacy. Not only efficacy could be influenced, but compatibility could also be influenced. I'm talking about physical compatibility. Sometimes when we've got a low pH, and especially when we're applying low water volumes, and you've got products in that spray tank that are already sort of on the border of insolubility, and you decrease the pH too much, that is the main cause of incompatibility. I can tell you that the main cause of incompatibility in South Africa, in any case, is very low water volume. So you limit the space for products to be solubilized. And the second one is too low a pH. And often these too lower pHs are not caused by buffers. They are caused by other products that we add to the spray solution that reduces the pH too much. I'm not going to say too much about this. This is Villiers 2 buffer products. The one on the left, probably the most well-known one, Komodo Buff, which is a normal organic acid buffer with nothing else in the formulation. So it's got a full rate of buffer in there. And AquaBuff Plus, which is also got very good buffering capacity, but it has a limited amount of surfactant in there. And this is where I'd like to give a warning even about our own product. If you're using AquaBuff Plus in certain fruit crops, for instance, where you need a very low rate of surfactant, it's fine. It will decrease the pH and will probably add, in some cases, sufficient surfactant. But this is not a product, for instance, that you can use on row crops and say, listen, yeah, I'm going to replace a buffer and I'm going to replace a surfactant, because the surfactant rate in this product is quite low for row crops especially. Okay, I said we can't talk about pH unless we talk about buffering capacity. And if I take you back to the beginning, we spoke about buffering capacity as the ability of water to resist a change in pH. And we said the main culprit is the anion called bicarbonate, or HCO3. So let me just explain this particular histogram. On the left, we've got pH. So both products' pH starts at just above 8. The blue bar, we've got low bicarbonate and low buffering capacity. the green bar, we got high buffering capacity. Say for instance, we're using a buffer in both these water sources, and this buffer is a bit iffy. It's a bit suspect about bringing down the pH. Water quality and buffering capacity can exacerbate that problem with that particular buffer, and I'll explain that why. If we look at the low buffered water, for instance, we add a certain rate of that buffer in, it's going to work fine. It's going to bring down the pH to pH of between 4 and 6, maybe around about 5. But once the buffering capacity of that water is high, it's going to expose the limitations of that buffer. And we're going to get a pH that is too high. It doesn't come down enough. And we're going to get alkaline hydrolysis. Conversely, and exactly the same explanation as just now, if we've got a buffer that we use, for instance, that is inclined to reduce the pH too much under certain conditions, this can happen. If we apply it in the high buffered water, it could bring down the pH to around about 5. But with this suspect product, this could happen. Same buffer, same rate, different water sources. And then you're going to sit with a huge problem with insolubility of products and incompatibility issues in the highest degree. So please use a quality buffer that you know can handle about all water sources. I'd like to show you an example, once again exactly the same as the previous slides, but what we've got now, okay, and those dotted lines are the target rate to which these buffers on their labels say that they bring the pH down to. So what we did is we did titration curves. So I'm going to show you 4 amounts of these buffers that we added to the water to see how much the pH would be reduced, and if it would be reduced to the right pH range. The water contained 150 milligrams per liter of bicarbonate, so it was sort of medium buffered water. Okay, let's see what happened. When we added 20 milliliters per 100 liters of water, this was below the registered rate range of both these products. 50 mils per 100 liters of water. And now we're moving into the registered rate ranges. 60 mils per 100 liters of water. And 100 mils per 100 liters of water. These are 2 products on the market, and you got totally different results with them. So it's important that the buffer you use constantly. It must be a good quality buffer, and you must make sure that it does exactly what you expect it to do. Okay, we're doing well with the time, and we are nearing the end. The last aspect that I'd like to talk about is turbidity of water. In Afrikaans, troebelheid van water. How dirty that water is, how muddy it is, the amount of organic matter that's drifting around in that water. So let's go for it. That is my best art, unfortunately, but that's supposed to be a water source on the left that contains a large amount of clay particles and maybe some organic matter that's drifting around in that water. Now we'll mix the stuff. We can even do a compatibility test in a jar beforehand. And we can see that everything mixes beautifully in this water, even though it is a bit murky or muddy. And we believe then that everything is fine afterwards. And that's my problem with these jar tests is that's as far as we go. We just look in the spray tank. But what happens further? If you think a bit further about what could happen here is as that droplet hits the leaf surface, it spreads out, dries out on the leaf surface, and what you're left with then, or what you could be left with then, is mud at the bottom there and the active ingredient lying on top. So that is what often happens with murky water, with turbid water. but I'd like to just give you a bit of a warning as far as incompatible tank mixtures. Like I said, the tank mixtures are getting more and more complex, and the water volume is going lower and lower, etc., etc. You can imagine if a bit of mud in water can have that effect and could limit absorption of a systemic product or another product. You can imagine that if you applying a tank mixture where products are antagonistic or at the leaf level, what they're going to do to each other. And this is often what happens. We do compatibility tests beforehand in a jar, for instance. Everything mixes well. It looks very, everything looks fine in the jar, but we never see what happens on the leaf. And this is where the reactions occur. This is where cations antagonize herbicides. This is where murky water has an influence. This is often where too low a pH has an influence on the solubility of products. So just be aware of that. This is an unknown phase, an unseen phase that we often discount and forget about. But it's probably the most important phase of products. A lot of crop protection products is on the leaf itself. Good, I'm basically finished with my presentation. I'd just like to summarize. And the first thing is that I'd like to say is we often talk about good and bad quality water, and I think that's a misperception. All water quality has got challenges. Any spray water has got challenges. So therefore, if we are applying a glyphosate or one of the other herbicides in hard and brackish water, we're going to get poor herbicide efficacy because of poor absorption into the plant. If we apply soft water, on the other hand, now if you understand the concept, soft water means low calcium and magnesium, but it can have high levels of sodium, or it's got low levels of everything. Soft water is normally the high foaming issue waters. Soft waters in South Africa are there various places, but canal water, for instance, sometimes in the Western Cape, the Eastern Free State, Natal Midlands, those are often soft water, whereas you go to for instance, in the Western Cape, for instance, you go borehole, a dam, for instance, and then the water quality is 10 times poorer. So I'm just talking about canal water specifically. And then, so both of them have got problems. Hard water's got issues, soft water's also got issues. Then high pH is alkaline hydrolysis of some insecticides could happen at a high pH. And probably some other issues as well that I haven't even mentioned today. But an unnaturally low pH could cause insolubility and incompatibility. And once again, I'd like to say it's normally not the buffers that cause these issues. It could be, it happens, but often it's other products that we are adding to spray mixtures that reduce the pH drastically. So 20, 30 years ago, we could get away with these type of mixtures because we were applying huge water volumes on row crops. So the water was enough to keep everything in solution. But these days, with lower water volumes that are being used, it's becoming more and more of an issue, especially in row crop and boom sprayers specifically. And then the last one, turbidity. It doesn't have advantages and disadvantages. It just has disadvantages. Dirty droplet residuals and poor efficacy. So sometimes people say they don't have a choice about what water source to use. I understand that, but then unfortunately there's going to be a reduction in efficacy of certain products with that water. The last slide, and just a bit of an advertisement before we end off, is about Villiers, or the Winfield product that's marketed by Villa, which is Class Act NG. Now, Class Act is an established name in the United States. So it's been around for a long time, but NG was basically one of the last formulations, and it stands for next generation. So it's a 4-in-1 adjuvant solution for spray mixtures. Now, I'd like to say something about Class Act NG. It contains enough, or a full rate of ammonium sulfate, to negate all that salt antagonism or cation antagonism, whatever you want to call it. It contains a non-ionic surfactant. It's not the same as Villa 51. It's another type of surfactant, but it contains a full rate of surfactant. So if you're applying at the 1 to 2% rate range, you're getting enough surfactant. It's got the corn sorb technology, which is a high fructose maize syrup extract, and that helps that spray droplets take a longer time to dry out on the leaf surface, and therefore you've got a longer absorption time. And then it's got an anti-foaming agent as well. But with all these components, it's got everything in there that is suitable for glyphosate. So that's our premium product, but obviously if the premium product is not used, the next product will be a Velocity Drymax. And if surfactants are included, then you must talk to your agronomist about that. And that's almost at the end. Don't go yet, because we've got a last slide after this, which is a competition. Thank you everyone for listening today. I hope it was insightful. I hope it was enjoyable to listen to. And if you have any questions, you are more than welcome to email me on that email address, or you're welcome to phone me as well, and I'll be happy to answer your questions. And we're going to end off on this slide. So thank you for joining today's webinar. Just let me put on my camera before I carry on. Okay, so thank you for joining today's webinar. We trust that this session provided valuable insights into overcoming spray water challenges to improve product efficacy and performance. Now, please feel free to leave your comments about the webinar in the comment section. It's always good to hear from you, and also kindly scan the QR code. You'll see on the slide there's a QR code, and then you will be taken to a bit of a competition, 3 questions that you have to answer quickly and then submit, and then you can win a very nice prize from Villa. So please scan the QR code on the screen now, and then go into the competition. And then lastly, please also look out for communication coming your way over the next few days with a short question and answer activity, giving you the opportunity to earn CPD points. So thank you everyone. It was really a pleasure having all of you in the session today, and please phone me if you need any more information, or email me. Thank you so much.
Thank you, Brian. Dr. Brian, donkey.
Plezier.
Brian, thank you very much for the presentation. Always great to listen to what you have to say.
Ek is nou al lank in die bedryf, maar so lees ek net altyd baie waarde, hoor.
Ag, ek is bly om dit te hoor.